Up to this point, we have seen how to obtain the solution of recurrence relations using characteristic equation in cases where the roots are distinct, so you do not have repeated roots. But what if you have repeated roots? You have roots with multiplicities greater than 1. So this is the general case if the characteristic equation given in this way has s distinct roots. Obviously, s here is upper bounded by k because you will have as many as k roots in the general case, r1 through rs with multiplicities m1 through ms. And obviously, if you add the multiplicities up, that should be equal to k. The solution to the recurrence relation corresponding to this characteristic equation, obviously, is given in this form. And k's here are, again, coefficients to be determined from initial conditions. Now, this looks like a complicated expression, but it's simply a simple extension of what we already have seen. You see, we would have k1 times r1 to power n plus k2 times r2 to the power n, dot, dot, dot. Let's say we have k roots, k sub k times r sub k to power n. This was the form, the general form. Now, if r1 is a repeated root, for instance, let's say r1 equals r2. In this case, these two would be the same term, but instead of this, if you have a multiplicity of 2, you would have k1 times r1 to n plus k2 times n times r1, well, r1 and r2 the same, to power n, plus k3 times r3 to n, dot, dot, dot. Okay, so the only addition is this n term here, and if it is repeated 3 times, in the third term, you'll have n squared. If it is repeated 4 times, in the fourth term, you will have n to power 3, and so on. So this appears here. Okay, so let's see this on an example. Let's say this is my recurrence relation, Tn equals 7 times Tn minus 1 minus 16 Tn minus 2 plus 12 Tn minus 3. It's a recurrence relation with degree 3. And I have 3 initial conditions here, initial values. And the characteristic equation is, of course, a degree 3 equation, r to power 3 minus 7r squared plus 16r minus 12 equals 0. If you factor this out, these are the roots, okay? And the roots are 3, 2, and 2. So 2 is a repeated root, okay? So the solution is going to be of the form k1 times 3 to power n plus k21 times 2 to power n plus k22 times n times 2 to n. Now, if 2 was a different number here, if the roots were 3, 2, and 5, I would have k1 3 to n plus k2 2 to n plus k3 5 to n. But since 2 is repeated, I have this n here. Okay? And if 2 was repeated 3 times, then I would have k1 2 to n plus k2 times n times 2 to n plus k3 times n squared plus times 2 to n. This would be the general form if you have a 2 as a repeated root with multiplicity 3. Okay, so you get the idea. At every repeated root, you add a factor of n to each of the components. Okay, therefore, the general solution is of this form. And the only thing that remains here is to find the k coefficients, and to be able to do that, just plug in the initial values t0, t1, and t2. This is the set of linear equations that you need to solve, which yields this: k1 equals 1, k21 equals 0, k22 equals minus 1/2. And therefore, just put them in this equation. You get Tn equals k1 equals 1, so that's 3 to power n, plus this, but k21 is 0, so this term vanishes, plus k2 to minus 1 half times n times 2 to power n.